Hello, calculus student. This video is for 4.6 part 1. We are looking at limits and infinity and asymptotes. The second part of it will actually look at how we can sketch a graph. But the important part is 4.1, limit and infinity. This particular technique will be used in calculus 2, so you need to know how to do these. So what is limit at infinity? We are looking at when x becomes sufficiently large. That means in a nutshell, x become like 1 million, 2 million, you plug in a very big number to f of x, and to see if f of x actually stabilize and become close to a number L. And if this happen, we say limit x approaches infinity, f of x equal to L. And then the other side would be when x approaches negative infinity. In a way, we say not x become very small, but actually negatively small, in that the absolute value is large, meaning we are plugging in x equal to negative 1 million, negative 5 million, really big number, and then we watch how f of x get close to, and if f of x become close to a particular value called L, then we say there is a limit for x approaches negative infinity. So this should be negative over here. There's a typo here. Which I have fixed in the real file, but I didn't fix it here. So this should be a negative infinity. Okay, so now these two numbers could be different. You could have a function where it approaches a number at positive infinity and it approaches a number at negative infinity. It could be the same also. So whenever one of these happens, it doesn't have to be on both sides. If one of these happen or both happen, then we say this number y equal to L is called a horizontal asymptote. And it describes the end behavior of a function. So in a nutshell, you can think of f of x, you graph f of x, there's some things here in the middle, maybe asymptote or whatever. But when it is really at the two end, then it stabilizes at a particular value. Like doesn't change anymore, it doesn't go to infinity like in a polynomial. And in this side, it can also stabilize to another value. So this is called the asymptote. Y equal to a horizontal line. So this is why you can have L1, L2, or you can have them being the same. Now, a lot of rational functions have this behavior. So how do I find this L, these limits? Because after I find this limit, then I know the horizontal asymptote, and it helps us to graph. One thing that we need to know after you go through pre-calculus material, you know that all polynomial does not have limit at infinity or negative infinity, but rational functions may have. So because all polynomial function either goes up on to two side or go down on the two side or go one, like drop to the left, rise to the right, like that. So polynomial infinity is always either positive or negative infinity. But for rational function, they almost, well, some of them don't have, but they will have horizontal asymptotes. Some of them. Okay. So how do I calculate this infinity? Because when you even when you graph it, sometimes you really don't know if they stabilize to a limit, right? So the basic principle is use the fact that if you have limit x approaches infinity, 1 over x equal to 0. That makes sense because if you have 1 over a really big number, big positive number, it would be a 0, right? And if you have 1 over a big negative number, when I say big negative, it's negative of the absolute value of x, right? Negative of a big number. It's very strange. It's negative, but it's a big negative, like negative 1 million. It is also 0, like 1 over 10 million, it would be 0. So these are the main principle that you use to do limit at infinity. The other three would be kind of by graph. We know that e of x graph is, maybe I'll use decimal. You look at the graph and you know that they have a vertical or they have a horizontal asymptotes at the end. So we can tell that it has here. Okay, so look at this graph, y equal to arctangent of x. maybe I'll put this up. Arctangent of x. So these functions, they have when you see them, they have asymptotes at the large side and they have asymptotes at the small side. So in a nutshell, if you don't have this just arctangent, it would approach us to pi over 2 on the positive side and negative pi over 2 on the negative side. So this is arctangent. The other one is e to the x. So this function everybody knows on the right hand side is shoot up because it's exponential. But on the left hand side, when x approaches negative infinity, is approaching 0. Okay. So the other one is when you have e to the negative x, which is the decay function, then when x approaches infinity is approaching 0. So these two, you can look at it from a graphical point of view to know that they have asymptotes. So they have when they have infinite limits. Okay, so let's look at our. So you would use these. Yeah, if you have arctangent x, when x approaches negative infinity is negative pi over 2. And then if you have limit x approaches negative infinity, e of x, that would be equal to 0. If the function shows up that related to those, you know that they have a limit and infinity. So for the most of the rational function, it is all using this. So how do I do this? Limits x approaches infinity 6x minus 1 over 3x minus 8. How do I use a 1 over x? So none of them has 1 over x. They have 6x, but not 1 over x. So what we do is we look at the highest degree of the exponent of x in the denominator and I divide every one of them by the same thing. So I would write it as 6x minus 1 divided by x, and then 3x divided by x minus 8 divided by x. Why do I subtract pick x? Because in the denominators, so then I would have a constant. Okay, I would have 3 minus 8 over x, 6 minus 1 over x. So anytime we see 1 over x of a limit, so by limit law, I can just go into each one of them. This becomes 0, right? So we'll say limit becomes 0 here. So that's equal to 6 over 3. And there's no direct substitution, but the limit when x approaches infinity would just be 6 over 3 equal to 2. Okay, so very easy. And then even if it's positive and negative infinity, it's the same. So what about this one? So the degree in the denominator is x squared. So I divide every term by x squared. 6 over x squared, no, 6x over x squared minus 1 over x squared over 4 x squared over x squared, and then this become a constant, right? So minus 5 over x squared. So if 1 over x equal to infinity, 1 over x times 1 over x is 1 over x squared. The limit will be infinity also, right? So x approaches positive or negative infinity of x squared would also be 0. So actually any power of 1 over x would be 0. So, and then we do limit of them. Limit. So it's kind of like distributed property limit. So this would be limit of 6 over x is still 0, right? Minus limit of 1x squared is 0. Minus 0. This is 0, actually. And then what about this? This is 4 minus a 0. So it is 0 over 4 is 0. So this limit and infinity is 0. So it would have a horizontal asymptote of y equal to 0. What about if I have a square root? Can I divide by x like that? And what about if it's negative x? If x approaches negative infinity, that means x is a negative number. So notice that square root of x squared is actually negative x if x is negative. Kind of like if you just imagine if your x is negative 4, right? You square it, it's 16. You take a square root, it's actually 4, not negative 4. So in order to keep the negative sign, you have to say negative x. So when you have a x approaches negative infinity, you divide it by x. So for x squared, the highest degree is x squared in a square root, but you divide it by negative x. So you will say 6 over, okay, so every single term divided by negative x outside, 1 over negative x. But inside, you would just divide it by x squared because square root of x squared is just square. So it would be 4x squared over x squared minus 5 over x squared, right? So this would be, 6x. The top would be negative 6 minus 0. The bottom would be square root 4. So I would have negative 6 over 2. So it's actually negative 3. So instead of 3, it's negative 3. The third one is we have 3 minus 2x squared. So this is the function, and I have x approaches infinity. Well, this is x squared. Anything over x squared is just infinite. That's equal to 0. So that's equal to 3. Okay, so the last one is this one. So the lowest exponent is in the denominator is x, so I divide everything by x. So I would say, okay, I would say the top would be x squared over x minus 2x over x plus 5 over x. The bottom would be x over x plus 1 over x, right? So the top would still be x minus 2 plus 0, but this would be 1 plus 0. Now I'm still doing limit x approaches infinity. So if I have, just ignore this would just be x minus 2, right? If you divide it by 1, and then if you have x approaches infinity, it's still infinity. So you could have, so this is the case where it's a rational function, but the function does not stabilize into a horizontal asymptote, so there's no horizontal asymptotes. You can actually look at this from the point of view of a pattern. You will see that if they have same degree, the asymptote is actually, or the limit is actually the ratio of the leading term. So ratio of the leading term, 6 over 3 is equal to 2, right? They're the same. If the degree in the top is lower than the degree in the bottom, then you always have 0. You can try other number. And this is different. And if you have the degree higher in the numerator than the denominator, you would have either infinity or negative infinity. You would not have a horizontal asymptote.